Okay, very good afternoon, my dear students. In the last class, we discussed the capacity calculation for various discrete channels. So today, let us discuss the channel capacity calculation for a Gaussian channel. Okay, so this is stated by Shannon and Hartley. So channel capacity of Gaussian channel is provided by Shannon and Hartley. So Shannon's capacity or Shannon-Hartley theorem, it states that the capacity of a Gaussian channel, states the capacity of a Gaussian channel whenever the information rate R is less than or equal to the channel capacity C. So wherever R is less than or equal to C, channel capacity is defined as the bandwidth log 1 plus SNR base 2. Here you can see that this R less than or equal to C. So it implies that it is a Shannon's theorem. So it is Shannon's theorem. So whenever the information rate is less than or equal to channel capacity, that is stated by Shannon. So this Shannon-Hartley theorem is valid only when R is less than or equal to C. Okay, whenever the information is less than or equal to the channel capacity, you can say that C is equal to, that is channel bandwidth, channel capacity is equal to bandwidth into log 1 plus SNR base 2. Now, let the distribution function of the noise P of n be in the form of Gaussian with mean is equal to 0 and various components sigma square. So let the distribution function of the noise be P of n. So what we are defining? We are defining P of n as a distribution function which is in the form of Gaussian. So I think you know that Gaussian is a bell-shaped distribution with mean as 0 and the various components sigma square, with mean 0 and variance sigma square. Then P of n is equal to 1 by root 2 pi sigma square into e power minus n square by 2 sigma square. So this is a Gaussian distribution. Here you can say observe that e power minus n square. So actually in the numerator you will have n minus m whole square. Here because mean is 0, you will get it as minus n square by 2 sigma square. Okay, so here we are defining the distribution function of the noise P of n be in the form of Gaussian with mean 0 and variance sigma square. So P of n is equal to 1 by root 2 pi sigma square into e power minus n square by 2 sigma square. But here the channel capacity is defined as the maximum of information rate. Okay, channel capacity is defined as the maximum of information rate or the mutual information. Okay, but we know the information rate relation with respect to the mutual information. Okay, so that's why we have directly represented as C is equal to maximum of R, because R is always less than or equal to the channel capacity. So information rate is always less than or equal to channel capacity. So maximum value of R, you can consider it as a channel capacity. Okay, so C is equal to, we can write it as maximum of R, where R represents the information rate which is defined as the difference between, here R represents the information rate which is defined as the difference between the information rate of the receiver, difference between the information rate of receiver to that of information rate of the noisy channel. So here R represents the information rate of the receiver upcoming from the transmitter via the noisy channel. So andukani that's why we have represented R as R of y minus R of n. So therefore for a transmitting and receiving channels of x and y and the noise added to the channel n, then the channel capacity is obtained as C is equal to maximum of R. So using this relation, so maximum of R of y minus R of n, first we will calculate R of n and similarly we will calculate R of y and we will substitute the difference in this expression, and maximum of the difference is nothing but our channel capacity, and you will get it as bandwidth into log 1 plus SNR base 2. Okay, so here where we are considering the noise distribution function as Gaussian. Okay, now upon solving this expression, you should get the channel capacity as bandwidth into log 1 plus SNR base 2. Now let us calculate the R of n value, that is information rate upcoming from the noisy channel, and R of y, that is the information rate of the receiver. Okay, so let us calculate these two parameters to get the channel capacity of Gaussian channel. Okay, now for that purpose, first we need to calculate the R of n. So what is R of n? R of n is the information rate of the noisy channel. So let R of n be the information rate of the noisy channel. So then we can define R of n as a product of sampling rate and entropy of the noisy channel. So R of n is defined as the product of sampling rate and the entropy of noisy channel. So we know that R is equal to sampling rate into entropy. So R is equal to Fs into H అని చెప్పి already మనం define చేసుకున్నాం. So R of n is defined as a product of sampling rate and entropy of the noisy channel. So let the entropy of the noisy channel be H of n. Now let us assume the noise to be white and Gaussian. So what we are doing? Let us assume the noise as white and Gaussian with a bandwidth of omega hertz. So what is bandwidth? Here the signal bandwidth we are considering as omega. Then for proper recovery at the receiver, the bandwidth should be 2 omega m, that is 2 into omega. So that's why sampling frequency will be 2 into omega. This is under Nyquist rate. So therefore, the information rate of the noisy channel R of n is equal to 2 omega into H of n, where H of n is the entropy of noisy channel. So let us take this equation as equation 2 and first calculate H of n. What is H of n? H of n is the entropy of noisy channel, which is Gaussian distribution, which possesses Gaussian distribution. Now, as the noisy Gaussian channel is continuous in form, the entropy of continuous signal is defined as the noisy Gaussian channel is continuous in form, the entropy of continuous signal is defined as H of n is equal to minus integral minus infinite to plus infinite P of n into log P of n base 2 dn. Here you can observe that, so whenever while discussing the discrete channels, we consider the integration as a summation that range from for example, if it has 3 elements, so it will be summation sum j is equal to 0 to 3 pk log p suffix k base 2 అని చెప్పి represent చేశారు. But here this Gaussian channel is continuous in form, so it is equal to minus integral minus infinite to plus infinite p of n into log p of n base 2 dn. So that's why we have considered we have replaced the summation as with integration. Okay, so now we obtained the H of n expression, and here we have replaced the summation with integration, and here we have assumed we have already assumed P of n as some probability of noisy channel. We have obtained it as we have assumed it as 1 by root 2 pi sigma square e power minus n square by 2 sigma square. Okay, this is our assumption. We have assumed the channel to be a Gaussian. So that's why we have instead of summation we have integration, because it is a continuous channel. And here mean is 0 and sigma square, if you observe, the sigma square is a variance component. Okay, now in order to get R of n, you need H of n, because omega is a known factor. Here omega is nothing but the frequency of continuous signal. In the earlier cases we considered this as a message signal FM, but here instead of FM, because the noise is also Gaussian, we have considered it as omega. So sampling rate will be 2 into omega. So that's why we have represented H of n with a integration instead of summation because it is a continuous channel. Now finally final thing is to calculate the entropy. Then only we can calculate the information rate R of n. Okay. Now please substitute the value of P of n in H of n. So please substitute the value of P of n, already assumed a Gaussian channel distribution, in H of n expression so that we can get the entropy H of n. Then you can substitute the entropy value in equation 2 to get the information rate R of n. Okay, this is a procedure. So let us calculate the entropy and you can calculate the R of n. So upon substituting the P of n inside the logarithm function of H of n. Now let us substitute P of n inside the logarithm function of H of n. H of n will be minus integral minus infinite to plus infinite P of n into log P of n base 2 dn. Okay. Please let us substitute P of n in this expression. But instead of substituting it outside the logarithm, please substitute inside the logarithm function. So log, please substitute P of n as 1 by root 2 pi sigma square e power minus n square by 2 sigma square dn. Okay. So finally we obtained this. Please replace P of n value inside the logarithm function. Okay. So log 1 by root 2 pi sigma square into e power minus n square by 2 sigma square. Only substitute the function, replace the function inside the logarithm. Outside the logarithm, don't replace the value of P of n because this is a simplified procedure. Okay. So instead of substituting P of n value outside the logarithm, please substitute inside the logarithm. So H of n will be minus integral minus infinite to plus infinite P of n into log 1 by root 2 pi sigma square plus log e power minus n square by 2 sigma square dn. Because it is in the form of log AB, we can write it as log A plus log B. So considering 1 by root 2 pi sigma square as some A and e power minus n square by 2 sigma square as some B, this is in the form of log AB. We can split it as log A plus log B. Now here P of n, now this, if you observe the first term, it is log 1 by root 2 pi sigma square. So this is in the form of log A by B. So log A minus log B, you can write it as log A minus log B. So log A is log 1, so that is 0. Okay, here you can see log A minus log B. So log of 1 will be 0 minus log root 2 pi sigma square. So here you can observe log root 2 pi sigma square as a valid value, but log 1 will be 0. Okay, so into dn minus, actually here you have negative sign. Okay, so minus is applied to the second term. So minus, and here inside the logarithm you have e power some minus n square by 2 sigma square. Now this power value, you can take it outside the logarithm as a product. So ఇక్కడ మీకు పవర్ లో ఏంటిది minus n square by 2 sigma square. You can take it outside the logarithm as a product value. So that's why I took outside the logarithm. So minus n square by 2 sigma square integral minus infinite to plus infinite. Here P of n is common factor. So that's why P of n into log e base 2, because e power value we took outside the logarithm, into dn. So it is equal to, so here log 1 is 0. Let us simplify the expression further. Log 1 is 0. Okay. So P of n into log root 2 pi sigma square base 2 dn. Okay. So minus of minus, it will be positive. So P of n into log root 2 pi sigma square dn. Okay. This is the first term simplified value plus n square by 2 sigma square integral minus infinite to plus infinite P of n into log e base 2 dn. Now if you observe this n square, this is a value which is dependent on n. So that's why we have to represent inside the logarithm. Okay, so that's why take the values of take the variable values which are dependent on n into inside the logarithm. Sorry, inside the integration. Take these parameters inside the integration. Okay, so therefore, upon further simplification, here log root 2 pi sigma square. Please observe the equation carefully. This log root 2 pi sigma square is a value which is independent of n. So that's why I can take outside the integration. And this n square is a value which is dependent on n. Please take it inside the integration. And the values which are independent of n, please take outside the integration. Here log e base 2 is independent of n. And also log root 2 pi sigma square is also independent on n. So that's why we can take these values outside the integration. Okay. So that's why we obtained it as log root 2 pi sigma square base 2. I took this as outside the integration. Now integral minus infinite to plus infinite p of n dn. So here if you observe this value, this is sum of all the probability values, sum of all the probability values of a particular event is 1. So that's why you can replace integral minus infinite to plus infinite p of n dn. You can replace this whole value as some 1 plus, actually here you have n square by 2 sigma square, but n square is a dependent value of n. So take it inside the integration and take this log e base 2 outside the integration. So that's why here you can see log e base 2 by 2 sigma square integral minus infinite to plus infinite n square into p of n dn. And in the first term we have replaced integral minus infinite to plus infinite p of n dn as 1. So first term final value will be log root 2 pi sigma square base 2 plus I took this log e base 2 outside the integration. So that's why log e base 2 divided by 2 sigma square integral minus infinite to plus infinite n square into p of n into dn. Okay, because I took log e base 2 outside the integration, being it as an independent value. Okay, now if you observe this value, think inside the integration, integral minus infinite to plus infinite, n square into p of n into dn is a variance. So this is an expression for a variance. So integral x square p of x dx is sigma square, that is variance. So now I can replace this whole value as sigma square, because integral minus infinite to plus infinite p of x dx value is 1. Okay, because here it is a noisy function, we can write it as p of n dn. Similarly, n square integral minus infinite to plus infinite n square into p of n dn is sigma square. Okay, so log root 2 pi sigma square plus log e base 2 by 2 sigma square into integral minus infinite to plus infinite n square p of n dn is some sigma square. Because that is a variance. Okay, so sigma square gets cancelled. Let us see the simplification. Here sigma square gets cancelled and 1 by 2 log e base 2. So here you have 1 by 2 log e base 2. Now if you take 1 by 2, that is half value which is outside the logarithm, it is in the product. So if you want to take that value to inside the logarithm, it will be e power 1 by 2. It will be e power 1 by 2. Amma, listen carefully. So half is outside the logarithm. So log e power 1 by 2 avutundi. If that product is taken inside the logarithm, you can consider it as log e power 1 by 2 base 2. Because sigma square gets cancelled. So ante ippudu meeku enti vastundi, second term will be log root e plus first term is log root 2 pi sigma square base 2. So first term is log A plus log B. Let us consider. It will be log AB. So root 2 pi sigma square into root E ostundi. So you can write it as root 2 pi E sigma square. So finally we obtained H of n, that is the entropy of noisy channel, as log root 2 pi sigma square base 2. Okay, so please remember this expression. Now let the noise power be capital N. So let the noise power be capital N. That is our assumption. Let us consider signal power as capital S and noise power as capital N. So noise power be capital N, which is defined as mean square value of the noise signal. Then you can write sigma square as, sigma square is a variance. You can write it as expectation of mean square minus expectation of mean whole square. So this expectation of m square is nothing but the mean square value of the noisy signal. Okay, so I can replace the first term as capital N, and expectation of mean m is 0. Mean value is 0. So that's why 0 square, it will be 0 only. So finally we obtained variance as capital N. It is equal to the noise power, that is mean square value of the noise signal. Now please make use of equation 2, that is the information rate of noisy channel, and let us substitute H of n in the expression of R of n. Because we have seen second expression. What is the second expression? R of n is 2 omega into H of n. So please substitute R of n as 2 omega into H of n. So 2 omega into log root 2 pi E sigma square base 2. Just I have substituted H of n value in the expression of R of n. So 2 omega into log root 2 pi E sigma square base 2. Now here inside the logarithm, if you observe carefully, it is log 2 pi E sigma square whole power 1 by 2 ostundamma. So I can take that power 1 by 2 as a product outside the logarithm. So 1 by 2 into 2 omega into log 2 pi E sigma square. But sigma square is n. That is same as noise power. So I can write it as omega into log, because half and 2 gets cancelled. So you will get it as omega into log 2 pi En base 2. Log 2 pi En base 2. Okay. Now please take it as equation 3. Please take it as some equation 3. Okay. So R of n is 2 omega into H of n, and taking this 2 pi E power E sigma square whole power 1 by 2, that power 1 by 2 outside the logarithm, here 2 and 1 by 2 gets cancelled, and you will get it as omega log 2 pi En base 2. Where log 2 pi En base 2. Now please consider this R of n, which is omega log 2 pi En base 2. Take this as some equation 3. Now what is the next thing? Now you need to calculate the value of R of y. Okay. So R of n is equal to omega log 2 pi En base 2. Take this equation. Now let us calculate the value of R of y. So what is R of y? It is the information rate at the receiver due to upcoming information from the transmitter via noisy channel. Let the signal power be capital S and the noise power be capital N. Now the output Y is a combination of both signal and noise. So instead of so you will get the same value of R of Y, but instead of N you will get S plus N. It is a combination of both signal and noise components. Okay, so 2 omega into H of Y actually here. Okay, this is H of Y. I will replace. So which is equal to 2 pi E sigma square. So everything is same except instead of signal power, you will get both, instead of noise power, you will get both signal and noise powers because it is R of Y. That is the information rate of a receiver. Now let us substitute the values of R of Y and R of N from equations 3 and 4. Please substitute the two equations in equation 1. What is the equation 1? Channel capacity C is equal to maximum of information rate. Maximum of information rate, which is equal to maximum of R of Y minus R of N. This is the original equation, which we considered as equation 1. So omega into log 2 pi E of S plus N. This is the R of Y. 2 pi E of S plus N. This is the first term. Minus, second term is R of N. What is R of N? Omega log 2 pi En base 2. Okay. So this, now once again this is in the form of log A minus log B. So I can write this as log A by B. Log of A by B. So omega log 2 pi E of S plus N divided by 2 pi En. Because this is, if you take omega as common, it will be some log A minus log B. So I can write this as log of A by B. So this is equal to omega into log 1 plus S by N base 2. So finally, if you observe this equation, we can conclude that channel capacity is omega log 1 plus SNR base 2. Okay, this is our Shannon-Hartley theorem. Therefore, Shannon-Hartley theorem states the capacity of Gaussian channel as C is equal to bandwidth log 1 plus SNR base 2. Here bandwidth represents the maximum frequency of the message signal or continuous signal. Okay, that is represented by omega. So in the earlier classes, we considered this as some FM. That is the maximum frequency of message signal and cheppi represent chesaru. But here we are defining it as some omega. Okay. Now, but actually, if you observe carefully this equation, actually our intention is to increase the channel capacity. Once the channel capacity is increased, you can transfer sufficient amount of data via the channel. So, in order to increase the channel capacity, please observe this equation. So, to increase the left hand side capacity, either you can increase the bandwidth or you can increase the SNR. Because channel capacity is dependent on omega and SNR. So you can increase either the bandwidth or the SNR to increase the channel capacity. Okay, but omega, that is the bandwidth, and SNR are once again inversely proportional. So to increase channel capacity, we can increase either omega or SNR. But once omega is increased, SNR will reduce. Okay, there exists an inverse proportionality between omega and SNR. So that's why we need to provide a trade-off between bandwidth and SNR to provide high channel capacity. So our intention is to increase the channel capacity capital C upon providing proper bandwidth and proper SNR. So sufficient amount of bandwidth and high amount of SNR. Okay. Now let us consider, if you observe the equation S by N, N represents the noise power. Already I told you N refers the noise power. It is defined as a product of noise power spectral density and bandwidth. Here noise power spectral density is represented as, considered to be white and Gaussian. So that's why its power spectral density is eta by 2. So many times we considered this expression. So N is equal to noise power spectral density multiplied by bandwidth. Here the bandwidth of the signal following under Nyquist rate is 2 omega. So eta by 2 into 2 omega. Here 2 gets cancelled. Here you will get the noise power as eta into omega, where omega is the maximum frequency of the continuous signal. Now please replace N value as some eta omega in the Shannon-Hartley expression. So omega log 1 plus S by eta omega. So maximum channel capacity can be obtained by applying omega tends to 0. Here, in order to get the maximum channel capacity, here you need to consider the bandwidth as a higher value. So apply the bandwidth limit the bandwidth to infinite, and so that you can attain the maximum channel capacity. So Cmax is limit omega tends to infinite. So same expression, omega log 1 plus S by eta omega base 2. Just to maximize the channel capacity, we have increased the bandwidth to infinite, so that lot of data can be transferred from source to the destination. Okay, so maximum channel capacity can be obtained by applying omega tends to 0. So same expression I have written here. Now let us rearrange this equation to express this equation in the form of limit x tends to infinite log 1 plus x whole power 1 by x. So this value is some e. Okay, so in order to rearrange the equation in this form, we have multiplied and divided with s by eta outside the logarithm, because here we need it in the form of log 1 plus x whole power 1 by x, log 1 plus x whole power 1 by x. Okay, so that's why we multiplied and divided with s by eta. So s by eta into eta by s into omega. Now here eta omega by s is outside the logarithm. So if you want to take inside the logarithm, you can take it as whole power eta omega by s. So outside the logarithm you have a product. So you can take it inside the logarithm as log the corresponding value power the product outside the logarithm. So eta omega by s, you can take it as power of the function available in the logarithm. Okay, so s by eta into limit omega tends to infinite log 1 plus s by eta omega. I took this eta omega by s into power. So eta omega by s. So I can write this eta omega by s as 1 by s by eta omega. So now this is in the form of log x tends to infinite. Sorry, limit x tends to infinite log 1 plus s by eta omega whole power 1 by s by eta omega. Now I can replace this whole as some e. So we can get it as log e base 2. So s by eta into log e base 2. Now this log e base 2 value is log e by log 2. You can get it as 1.44 s by eta. So from Shannon's theorem, r is less than or equal to c. Okay, and so what is the value of r maximum? Maximum value of information rate is the channel capacity. Okay, and you can increase the channel capacity when omega tends to infinite. So from Shannon's theorem, here r is less than or equal to c, and therefore a trade-off between bandwidth and SNR can be obtained by the relation r max. So here, because r is less than or equal to c, maximum value of r is the channel capacity. But we need to maximize the channel capacity. That can be done by applying omega tends to infinite. So limit omega tends to infinite c. That is the channel capacity. So it is 1.44 s by eta. So r max is limit omega tends to infinite the channel capacity. So it is 1.44 into s by eta. So this relation shows the bandwidth SNR trade-off of the Shannon-Hartley theorem. So this Shannon-Hartley derivation is very, very important, and this trade-off is also important for your examination. Okay. With this almost all we have completed our 4th chapter, and I can show you where I have uploaded the documents regarding your 4 chapters. Did any one of you check the files of your 4 chapters? See, in the Teams, you have entered the digital communications channel. So here you have posts followed by files followed by notes. Here go to files. In these files you can see DC unit 4, 3, 2, 1. Okay. Please okay, here you can see I have uploaded all the modules of 4th chapter. So 6 modules are available and similarly problems I have uploaded. So almost all the similar models which we have discussed in the class. So I have uploaded here, you can check this. And this PDF is the handwritten material which is provided by your seniors. So at the time I told this subject, so they have written the notes. Okay, this is like your friend's material only. And these 6 are the corresponding modules of PPTs which is available. Okay. So like that I have uploaded 4 chapters material. You can check it in files of digital communications. Okay, I don't upload in the WhatsApp group. Please, because sometimes you may not download it or there will be any misplacing. So in order to avoid such kind of problems, directly you can check the digital communications and files you can see. Okay, there you can see all the modules, all the chapters and its respective modules. Okay, so I have completed the 4th chapter. From next class onwards, we can see the discussion of 5th chapter. Okay. So any doubts in the today's class?